Hello everyone. Today we are going to talk about a disjoint set data structure, which we will be more familiar with union find operations. So let's see what disjoint sets are. So two sets are called disjoint sets if they don't have any element in common or the intersection of those two sets are null. For example, you see here we have like 4 sets here, right? And you see the values in each of the sets are like unique. So basically there is no same value between any two sets. So we can call these 4 sets as disjoint sets. And then you can see that for each set, we have one value in color red. So we can say that that value is the representative of that set. So we can say this is set 8. So we can say the name of this set is 8. The name of this set is 9. This is 1. This is 5. Okay. So this is the definition of disjoint sets. Now, disjoint set data structure supports these following operations. Like first one is adding new sets to the disjoint set. So suppose we have 4 disjoint sets and then we can add another disjoint set, say 0. Okay. So this is operation 1. And then let's go to the next operation. That is merging disjoint sets to a single disjoint set using union operation, this one. Okay, so what we can say is we want to merge these two, right, 9 and 16, and then they become a new set. And say 1 becomes the new representative. That means 1, and then 6. Okay, so this is an union operation. Like this is union, you can say union of 9 and 1. 9 was the name of this set and 1 was the name of this set. After we union them, then it becomes new set, the new merged set or becomes 916 and the new name is 1. Okay, and then find the representative of a disjoint set using find operation. So let's say if I do this, find 7. Okay, in that case it will return me, it will give me 5. Okay, so the find operation is given any set member or set value, we find the representative of that set. In this case, the representative of set was 5, so 5 will be returned. And then check if 2 of the sets are disjoint or not. So someone says, okay, check between say 6 and 7. Okay, so what we do is we do a find 6. So this is operation number 4, and then we do find 7, and then we see that find 7 gives us this one gives us 5 and this one gives us 1. So these two are not equal. That means 6 and 7 are in 2 sets that are disjoint. They are not in the same set. Okay, so these are the operations on the disjoint set data structure. Now, say, let's try to be a little bit more formal. How can we represent this data structure? Well, we can see these data, each set as a tree, where the root of the tree is the set name. So say here, right, we can see let's say the first one. For the first one, we can say this set will look like a tree, and 3, 7. Okay, so this set can be represented as this tree, where the root of the tree is the representative of the set. So the observation here is this tree is a little bit different than the tree we are familiar with. That means the tree that we so far are familiar with, they actually have the top-down approach. That means, first of all, they are not directed edges, and then it comes down from the root to the bottom, whereas here it's kind of reverse. So you see from the down, the arrows go upwards. So if someone, so we can say this is an up tree, right? So you can see the arrows actually go upwards. Okay, so here in this example, let's say here in this example, initially say we had like 7 disjoint sets. Initially we had 7 disjoint sets. So we can say like each of these sets had just one node. So even with one node, that's a tree, right? Okay, and then there were some operations. Say the operation was like union of say 2 and 1, right? That created a tree like this. And then there was say union of 5 and 6 that created a tree like this. Then there was a union of say 4 and 7 that created a tree like this. And then there was a union of say 6 and 5 and 7. Then we got a tree like this. Okay, we'll come in details, but for now, we just are showing you that these joint set data structures can be shown with trees, where the root of the tree is the representative of the set. So how do we, if it's a tree, like tree kind of structure, then how the find works? So here we see like 3 disjoint sets, right? So for the first one, the representative is 1, right? This is the representative. For the second one, 3 is the representative, and for the third one, representative is 7. So if someone says like find 6, since this is up tree, what we do is we start from 6 and then we go up using the arrow. And then we actually have to reach the root, and it will return me the root. Okay. So find x follows x to the root and returns the root. That is the find operation. And the union operation is, suppose if you have say union ij, then assuming that I and j are roots point I to j. So this is the simple way of doing union, like pointing I to j. So someone says a union 1, 7, right? What I will do is I will just point 1 to 7. Okay, and now they become just one set. These all become one set, right? And 3 remains a different set. Okay, so we have learned about the structure of the tree, but how do we implement it? Because in the traditional tree, we saw like parent-child kind of relationship, and then we can use create data structures according to different languages, right? With nodes, every node has value, and then it has 2 links to, or 2 or multiple links to its child. But in case of disjoint set, we see that each set can be represented using a tree, but these are like up trees. So how do we actually represent them more formally? So one simple implementation is using an array. Okay, so let's look at this array. Initially, say this initially this disjoint sets are like this: 1, then 2, then 3. Okay, let's say from 0, 0, 1, 2, 3, 4, 5, 6, 7. So initially we had say 8 disjoint sets, and then we did these operations: union 1 and 2. Okay, or I think easier would be if I show on this same thing. Let me just remove the links for now. Okay, so initially all these were like disjoint. 1, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so we had this initially. Then we did this. We did union of 1 and 2. And okay, so union of 1 and 2, we can say, or let's do this. Okay, so let's say if I do union of, I can actually do both ways. So if I am doing union on I and J, it will create a tree like this from J to I. Okay, so from the first element to the, sorry, from the second element to first element. Okay, so if I do 2, 1, what happens? Then there's a link created like this, right? So this one becomes the tree and the representative for this is 1. Okay, initially, let's start, go back one step. So initially, you see these 8 disjoint sets, they are each a tree, right? And we know we can build trees with just one node. And so the representative of each of these trees were themselves. We can put them in an array, parent array, where the parent array represents the root of the tree they are in. So initially 0 was in its own tree, so it was its own parent. 1 was its own parent, right? Similar 2 was its own parent, 3, 4, 5, 6, 7, right? So this is the index. This is the index. And these are the root values. So initially, every set was a parent of itself, or you can say like root of itself, right? Parent or root. Then we do this, like union ij creates a link from j to I. So once I did union 1, 2, there was a link created from 2 to 1. And what happens is, I have to change the parent of 2, like at index 2. Now this new parent becomes 1. Okay, so because now these sets, like set 2's representative is 1, the root is 1, so I change in the parent array. So basically I am representing the tree using an array, and then I do union of 6 and 5. Okay, so what happens is, okay, so okay, so actually let's change this. Let's go back to the previous, like the previous one. So if there is a union of I and J, it points from I to J. Okay, so let's change this to 2, 1. Okay, so union of ij creates a link from I to J. Okay, so we did 2, 1. So 2, 1 actually created this link, right? So now the root becomes 1, that is fine. Then we do union of 6 and 5. So from 6, there's a link created to 5. So 5 is going to be the representative of this. So 5 is going to be the root for 6 as well, right? Index 6. And then we do a union of 4 and 7. If I do that, there's now 7 becomes the root, and so 7 becomes the representative at index 4, right? Next, union of 6 and 4. Now you see, if I do a union on 6 and 4, if I say 6, now 6 is, it goes to 6, right? The representative is 5. And for 4, you see the representative is 7, right? So basically this one translates into union of 5 and 7, okay? And then what happens is, yeah, from 5, there's a link created to 7. And now this thing is also changed to 7. Because 7 is now the root for 5, or the representative of 5. So using an array of indices, we can easily represent a tree representation of disjoint sets. Okay, now here is a bad case. Okay, so what is a bad case? So let's look at one thing here, and this is very important. So if I say, suppose union of 6 and say 2, then what happens? Then for 6, I have to find the representative, right? So the representative here is, you see, it says 5. It says 5. And for 2, it says 1. That means it becomes a union of 5 and 1, right? Okay, so if I go to 5 again, it now gives me 7. So union of 7. And if I go to 1, it also gives me 1. So now it becomes union of 7 and 1, right? And from there, you see, for 7, it's 7. And for 1, it's 1. So basically, from 7 to 1, I have to create a link or something, okay? So this is, we are following a convention where if we are doing union for, say, 2 elements, we try to create a link from the first element to the second element, right? This is the simple rule we are trying to follow. But if for the first element or even the second element, the representative element is not itself, then we keep on trying to find the representative element, right? So if someone says union of 6, I go to 5 and then I go to 7 and then I return 7. That's exactly what we did. From here we came here, then we came here, and eventually we just did this union, right? Okay. Now let's see if we follow this convention of union, that from the first one to second one, we create a link. In the worst case, what may happen? So you see we have like n disjoint sets here. And then what we do is we do union of 1 and 2. So this happens. This is created, right? Okay. Next, what we do is we do union of 2 and 3. Okay, then 2 points to 3, right? Next we do is say union of 3 to 4, right? So we are actually creating, doing it sequentially, 1 to 2, 2 to 3, 3 to 4, right? So basically after doing this, like n minus 1, union of n minus 1 and n, it becomes a chain, 1 to 2, 2 to 3, 3 to 4, right? Okay. Now the thing is, although each of the unions were like order of 1 operation, each of the unions, because they were straightforward, from 2 to 3, there was a link created. That's it. But the thing is, the find becomes order of n. So say here someone says, okay, find 1. And we know find actually returns what? The root of the tree. So from 1, I have to go to 2, and then I have to go to 3, then I have to go to up to n, because this is the root of the tree. So this returns n, that is fine, but my find operation becomes order of n, right? So can we do any improvement? Because we, in our implementation or applications, we need to do a lot of finds. So yes, so we can obviously do better. So there are actually there are different techniques, but I am going to discuss two. First one is union by size. So what it does is it improves union so that find only takes the worst case time of order of log n. Okay, so from n, order of n, I want to change find to order of log n, and I do that using some union, like some optimization on union. And the second technique that we are going to discuss is path compression. So in this case, we improve find so that the union by size and find, both of them become almost order of one. This is very interesting, right? So we are trying to do optimize union so that finds become better. And then we also want to optimize find so that both union and find become better and becomes almost order of one. This is very interesting how we are going to do this. So union by size. Okay, so what union by size is? Union by size is when you have disjoint sets, that means each of the sets is a different tree, right? So we also keep track of the size of those trees. And then what we do is, whenever there is a, whenever there is a union between a small tree and large tree, we always point the smaller tree to the root of the larger tree. Okay, so if someone says union of say 1 and say 5, in that case what's going to happen is 5 is in this tree, right? And 1 is here. And we see that the size of the trees, the current size of this tree is 4, and this is 2. So we point the smaller tree to the larger tree. This is what we do. And now the new size of the tree is going to be like 6, right? So how this technique is actually going to help us, let's see. So let's do the same practice again. We had like we did before, right? We have like n disjoint sets at the beginning, and then we do a union by size. We're calling it S union. Initially 1 and 2. Okay, so from 1 to 2 there is a link created. That's fine. Next, we do a union of 2 to 3. So previously what we are doing is we were just from 1 to 2 and then 2 to 3. We were just creating another link from 2 to 3, right? Instead of that, this time you see the size of this tree is 2 and the size of this tree is 1. That means the smaller tree always links to the larger tree, right? So you see that's exactly what we are doing here. The smaller tree is pointing to the larger tree. So the new tree is going to be this after 2, 3. Okay. And then we are going to do what? Union of, say, union of 3, 4, right? If I do union of 3, 4, 4 is going to be here, right? 4 is going to be here. So you see the size of this tree where the 3 is 3 and this size is 1. That means 4 will now point to the larger tree. Okay, so if we keep on doing this every time, every node is going to be point to 2. Every node, right? 4 is going to be pointed here, 5 is going to be pointed here, right? So after doing the nth, like unioning n minus 1 with n, these two will look like this, right? And now you see how good find is. Like any find will give you order of 1, because if you say find 4, right, it will just 4 is here, right? It will just go here and done. It will give you 2. If you say find n, it will just immediately go and give you 2, right? Okay, so this is, so you see how fast find becomes if I do union by size. If I keep track of the size of the tree and always link the smaller tree's root to the larger tree's root. But this is a, like, I would say this is the best case, but let's see what happens in the worst case. So in the worst case, what happens is, instead of union 1, say 1, 2, then 2, 3, 3, 4, right? 4, 5, instead of sequentially getting the union like we did here, instead what's going to happen is the unions are going to be like this, say union of 1, 2, then union of 3, 4, union of 5, 6, union of 7, 8. Okay, and then we do union of, say 1, so we are actually slowing it down, 1, 3, then union of 5, 7, okay, and finally union of, say 1, 5. So that means the whole disjoint set becomes one set, but in a slow, not sequentially. It will just, first half of them are going to be linked together. So that means n over 2 unions happen. So initially we had like n disjoint set, then n over 2 unions happened. So suppose 1 got linked to 2, 2 got linked, sorry, 3 got linked to 4, something like this. Okay, okay, done. So let's say we call it, say, okay, so this is okay. Now we do other unions. So use next step, we do a union between these two. What happens? This one is this, and this one is this. Now you see both of them had size of 2. So if both of them has same size, since we are doing union by size, we break the tie arbitrarily because both of them have the same size. So any one of them, so this one points to, so this one points to this one. Okay, that's how we get this one becomes this. Okay, similarly these two becomes this, these two becomes this, these two becomes this. Okay, next what we do is we have something like these two, right? If we union these two, what are you going to have? Both of them have size of 4. So we're going to have something like this, right? And this becomes this, right? Okay, so this and this becomes, let's call it, say, A, and this is B. And then finally, if we do another union, now you see this is A and this is B, right? These two are now joined. So if we do like this, this is the worst type of union, so that you see the find operation is no longer, so it's not flat anymore. Previously what happened is everything was flat, so you see like after all the unions it looked like this, right? Very flat. But this time it's not flat, we are actually gaining height. But in the worst case, how much height we may get, and as long as we are gaining height, the find becomes less efficient, right? You remember in the like most naive way of union, the height was so long, right? Was getting so long, order of n. And for this one, it became like, although we did union by size, it became so flat. But then we are trying to say that Okay, so this was a like a very feel-good situation, right? But there are cases where we can gain height. The tree may get height, and this is the worst height that the tree may get, right? So where half of the set elements, disjoint sets are going to be union together, and then next half like that. Even in that case, you see that every time like we are gaining height of 1 here, and then another 1 here, right? And then another 1 here, and finally how much height we get? 1, 2, 3, 4. Do you see that? So the maximum height, if someone says find this, if someone says find this, then you have to go like how many steps? 1, 2, 3, 4 to return this, right? To return this. That means even in the worst case, your find becomes, so if someone says, say this is z or something, and this is the root. If someone says find z, this one will take 4 steps, right? Which is log of n. Okay, so that means if we do union by size, find becomes order of log n operation. So this is much more better than, yes, in the best case, find will become order of 1. This is the best case, but this is the worst case. And we know the worst case is the time complexity of the algorithm, right? So instead of order of n, now by doing union by size, find becomes order of log n. Okay. Now, how do we implement this? How do we implement this? So initially we said like we have this parent, we can put like the tree representation can be smartly done using an array, right? We showed you one example, and then we keep another array, which we call size. Okay, so let's do this thing. Okay, so we actually have like 0 to 7 elements. So let's cross this. So we don't have this. So we have 2 arrays of size 8 each. Okay, so let's say the parent of what can I say after this? Okay, so let's do this. Yes, erase the links first. Initially, we assume that everything is disjoint. So we have 8 disjoint sets, right? We have 8 of them. And initially, each of them are trees by themselves. So one is represented, one's parent is 1, sorry, zero's parent is 0, then 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now we are doing union by size of 2 to 1. Both of them are of size 1. So we just break the trie arbitrarily, and this is what we get. And then we do again union by size of, say, okay, so 2 to 1. Then what happens is at the second index, 1 becomes the new parent, right? Okay. Then we do union of, say, 6 and 5. So for 6, the root is 6. For 5, the root is 5, right? Parent is 5. So we create a link from 6 to 5, right? Okay. So we join the root, and from 6 to 5, there's a link. And then we do union by size of 4 to 7, right? We go to the 4th element, we see the parent is 4, and we go to the 7th element, the parent is 7. So we do here this, and this becomes this. Okay, next we do union by size of oh, okay, so we didn't actually keep track of the size yet. So initially everything has the size of 1, right? Everything had the size of 1. And then when we did union by size of 2 and 1, right? 2 became the root. So what we do now is I just change the size to 2. The size becomes 2. And then 6 to 5. So we say that the tree that has a root at 5 has a size 2 now. We did union by size of 4 and 7. So the tree that has root in 7 now has a size of 2. Okay. Now next we do a union of 6 and say 4. 6 and 4. So union of 6. So 6 says we go to 6 and see its parent is we had actually changed. We had to change 6's parent to 5. Okay, and we had changed 4's parent to 7 because we had done these unions, right? Okay, so we go to 6 index and then look at the parent. It says the parent is 5. So it becomes union by size of 5. And we go to 4 and we see parent is 7. So it becomes the union by size of 5 and 7. So this time we go to 5. We go to 5 and then see, okay, the parent matches. That is fine. And then we go to 7 and we see the parent matches. That means from 5 to 7, there is going to be a link. Now, actually, we cannot say that. So there is going to be a link between 5 and 7, but since we are doing union by size, we have to link the smaller one with the larger one. Now we see the size of 5 is 2 and size of 7 is also 2. That means we have to just break tie arbitrarily. So we do this, and now you see the tree represented by 7 has a size of how much? 4. Do you see that? Okay. Next, say we do union by size of say 2 and 7. Okay. So this translates to we have to do a find of 2. If we go to the second index, you see it says your representative is 1. And then if you go to say 7th index, it says, oh, your representative is yourself. That means this is the root. Okay, so then it goes to union of 1 and 7. If I go to 1, it says, oh, your own representative is yourself, and 7's representative is himself. So there is going to be a link between 1 and 7. Now, what is the size of the tree where 1 is the root? It has a size of 2, right? And what is the size of the tree that has 7 as root? It has a size of 4. That means from 1 to 7, from a smaller one to the larger one, there is going to be a link, right? And now you see the size of the tree that is represented by 7 is going to be 6. So here are a few things. Like, although we are smartly using these arrays, right? Although we are smartly using these parent array for the root of the tree and size for the size of the tree, some of these entries are not correct. So suppose here you see that for 2, it says the size of the tree is 1, but we don't need to worry because when we say find 2, actually we don't look at this. What we try to do is we just check the parent of 2, and then we check if the parent of 2 is a different one. If it's a different one, then we go to that index, right? And then this time the parent has changed to 7. Then we check again. We see the parent is a different one. So we go to index 7, and now the parent matches. Only when the parent matches, those sizes are valid. So this is a valid size. Okay. So this is an implementation of union by size using a parent array and a size array. Now, the second way to do optimization, we say we have already showed that if we do union by size, that helps the find operation. Find now becomes order of log n. Okay, so what about doing some optimization when you are doing the find? Obviously, you can do that. So this is the optimization. Say at some point, your tree looks like this. Okay, then you want to do a find of 3. And do we know if we are doing a find of 3, we go all the way up until we reach the root, right? How do we know that we have reached the root? I already showed you that if we use a smart array, we keep on going to the index and we check if there is a index where the root is itself. So for the index 7, the root is also 7, right? So in that case, we can say, oh, we have reached the root. Okay, so what happens here is from 3, it goes to all the way to 7. So this is going to return 7, right? That is fine. But then what it does is, so how many steps it took? 1, 2, 3. Now we know that if we have created this tree by union by size, this is kind of log n operation. So after log n steps, suppose in the worst case, after log n steps, we got 7. We got 7 a root. Okay. So next what we do is, we are not done here. What we do is we just erase this link and create a direct link to the root. So what happens is the next time, if someone comes and asks like find 3, now this time there will be it will be returned in 1 step. Right? So this is the path compression. That means, yes, initially I may have to do like go through multiple steps for the find operation. I may need to go to log n steps at most for the find operation, but after the find operation, I just erase the link and create a direct link so that next time the find operation becomes even faster. So say we do like multiple find on this, find. So 10 of the finds. What happens is, if you keep on doing that, suppose we do find of 9. So this one actually found 7 in 2 steps, but what it can do is after that finding 7, it can just erase this link and create a direct link to 7, right? Okay, so that means for each of the find operations, we cannot say like how many steps it will need. We can say that in the worst case, it will need log n steps. But in future, if you do a lot of find, you will eventually get more and more efficient. In the best case, every find will be order of 1. But we cannot just say it will be order of 1. Rather, what we say is the complexity of find is going to be order of log star n. So what is log star? Log star n is it's a time complexity which is almost order of 1. Like it's almost order of 1. So I'm going to show you how it's not almost order of 1. So if you remember about the log step, so we said like what is log of 16 is 4, right? So what does it mean? It means that how many times you have to divide 16 to come to say 1, right? So you see So from 16 we divided and it became 8. Then we divide 8 again, it became 4, right? We divide it again, it became 2, and then we divide, it becomes 1. So how many steps? 1, 2, 3, 4 steps, right? So that's why log 16 is 4. That is log. Now what is log star? So log says how many times you have to divide with 2, where log star says how many times you can just apply log on something so that it becomes 1. So say if someone asks you instead, if someone asks you, say, what is log star of 16? It means that you have to apply, instead of, you have to apply log 2 on 16. What is that? 4. And then again log 2 on 4. What is that? 2. And then log 2 on 2 is 1. So how many steps? 1, 2, 3, right? So log star 16 is 3. Okay, so even for very large number, log star is maximum 5. Okay, so it means that if your tree has like 65,000 nodes, even in that case, in the worst case, your find operation will take at most 5. It has to go 5 steps. Why? Because because we are doing path compression. Okay, so we are doing path compression. And here is the thing. If you improve on find, that actually helps you improve on union as well. How? Because say, if someone wants to, suppose if someone from here, if someone wants to union of say 2 and 3. So do you see that union of this actually, first for this, actually you have to do a, like A, you have to do a find of 2, and B, you have to do a find of 3, right? So find of 2 gives you 1, find of 3 gives you 7, right? And then you do a union between 1 and 7 based on the size, and based on the size, the smaller one actually creates a link to the larger one. But the thing that I'm trying to say, that the like the efficiency of union also is dependent on the find. So if find is very fast, if this is order of, starts becoming order of 1, this one also becomes order of 1, then the union itself is also going to be order of 1, right? Okay, so that means now using the path compression, not only finds starts becoming like more and more efficient with time complexity amortized. So this is called amortized time complexity. The reason behind that is amortized means over time. So you cannot just say that immediately my time complexity is going to be order of log star n. This is over time, because over time your tree becomes, from here the tree looks like this, right? So this was the tree, and then after doing one find operation, this is the tree it looks like. So amortized means after over time, your average complexity is going to be log star n. So your union and find both are going to be more efficient. Okay, so here is one thing. The actual time complexity is the actual time complexity of find is actually order of This is the actual time complexity, amortized complexity, order of this. This is called Ackermann's function. So this is called Ackermann's function. This is the real-time complexity after the path compression. But this is the beyond the scope of this syllabus. We're not going to explain how this is this. The only thing that I can tell you is this is even slower than order of log star n. So you know that order of n can be written as order of n square, right? Because order of n is smaller than order of n square. So any algorithm that is order of n can also be said that this is order of n square algorithm, because that's true. Similarly, the true complexity is order of alpha n, which is the Ackermann function, but this is slower than order log star n. So we already understood what log star is. So to make it more clear and visible to everyone, we just order of Ackermann's function, we call it as log star n. Okay. Okay, so that's it. We talked about the disjoint data sets, and then we talked about union and find and optimizations on union find. Later on, we'll come back with problems with disjoint data sets and disjoint sets and union find operations. And solving some of those problems actually will clear up all your concepts. Thanks, everyone. Till next time.